That's the scale of them. It's a big-ish one, that. But if you think about it, I mean, so there's a number. It's called the Schwarzschild radius of the thing. So if you took our sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk within a radius of 3 kilometers, about 2 miles. So you've got to take this thing, which is what I have to convert from kilometers to miles, don't I? But it's about
that's okay. Just say kilometers.
700,000 kilometers. So it's about 500,000 miles radius or something like that. The sun. So you squash it down till it's about 2 miles, and then that would form a black hole.
Wow.
The 6 billion times the mass of the sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is, I don't know, larger than our solar system, basically.
Oh,
this
my
thing
God.
that sits in a galaxy. So we've got these 2 photographs.
Larger than our solar system.
Yeah, the event. Right. So it's a big structure.
Oh.
That's a Chandra X-ray image of. There it is. That's it. So the that one there, that's the M87 black hole. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way. So you think Saturn's rings. So this material is very flat. But what you're seeing in that photograph is the light rays being bent around the black hole from that flat disk. So that was a prediction from Einstein's theory, basically. He published it in 1915. And you can predict that that's what one should look like. And then just about, what was that, 4 years ago now, maybe 5 years ago, for the first time in history, we get an image of one, and it looks like the prediction. So It's a remarkable thing.
How phenomenal is that?
Yeah. So we've had those 2 photographs. The other thing we've had is so-called gravitational wave detections. So these are colliding black holes, and they collide and merge together. And obviously that's quite a violent event in the universe. And so that event, that process ripples space-time. So it sends ripples out in the fabric of the universe, space and time. And actually Kip Thorne is I've spoken to him several times. He's one of the greats, right? Won the Nobel Prize for this. And he calls it a storm in time. So you get a time storm. So really, we're to think, as we speak now, there will be these very tiny ripples from violent cosmic events passing through this room. And they're changing the rate that time passes. So that as they go through. And we can detect that now. So we have detectors that can pick that up. And so we've seen those collisions as well.
So these collisions, how far away?
Oh, millions of light years away.
And they're affecting what's happening in this room right now?
Yeah, to a tiny extent. So there's an experiment called LIGO, which is the, what it stands for, something like gravitational interferometer. That's a scale. I can't remember exactly what but basically, it's laser beams. There's a number. And there's one in Washington State, north of Seattle, and one in Louisiana. And they're kind of laser beams, 4-kilometer long laser beams at right angles. And they can detect these very tiny shifts in the, effectively, you could say the length of the laser beam. It's a bit more fiddly and complicated, but it essentially measures the distortion in space-time caused by these ripples. And it's way less than the diameter of an atomic nucleus, by the way, way less. These little sort of...
Oh, my God.
And so we've observed many of those collisions. There it is. There's LIGO. Wow. So it's just basically 2 laser beams but with these ultra high precision thing. And so we've got data now of the collision of black holes and those event horizon pictures with radio telescopes. So that's part of it. But the main bit has been theoretical advances in understanding exactly... in a sense, it was what's wrong with Stephen Hawking's calculation, which is a weird thing to say sometimes because people think Stephen Hawking surely didn't get his math wrong. But he did, actually, in his calculation. So what he calculated back in 1973, 1974, is that a black hole, so we picture this thing from which nothing can escape, even light. So when you go in, you're gone, basically. What he calculated is that even though these things are just a distortion in space and time, that's the description of them. So it's almost as if there's nothing there apart from a distortion in space and time. He calculated that they glow, so they have a temperature, so they emit radiation. It's called Hawking radiation. And so important was that discovery. If you go to Westminster Abbey in London, look on the floor of the Abbey on his memorial stone, and he's in there next to Newton and Shakespeare and all these people, and he's there. And chiseled in stone on the floor of Westminster Abbey is his equation for the temperature of a black hole. So it was this tremendously important discovery. So he discovers these things glow, and he calculates how they glow. They're very low temperature, but they emit things, which means that they shrink because they're emitting stuff, and so they're shrinking. So that means they have a lifetime. So first of all, one day they'll be gone. So that means that you have to address this question of what happened to all the stuff that fell in. And his calculation said that there's no record at all of anything that fell in all this radiation that's come off the black hole. So it's purely information-less radiation. So what that means is that black holes destroy information, according to that calculation. And that's a big deal because nowhere else in all of physics does anything erase information from the universe. So it's really true that if I got this notepad and pen, right, and I wrote some things on it, and then I set fire to this, even just incinerated it, put it in a nuclear explosion, whatever. In principle, according to all the laws of nature that we know, if you collected everything that came off, all the radiation, all the bits of ashes and things, and you could just measure it all, then just in principle, the idea is you could reconstruct the information. So it all gets scrambled up and thrown out into, and so in practice you can't do it. But just in principle, the laws of nature say that information is not destroyed. It's just scrambled up in a way that you can't reconstruct, right? But this calculation that Stephen did said there is no information in that radiation at all. Zero, just nothing. So it seemed that uniquely in the universe, black holes erase information.
Welcome to Betfred Gaming. Immerse yourself in over 1,000 games. With great sign-up offers available, love gaming, Betfred.
You, just you, building your app on Base 44. Describe it. And it's real. One thought leads to more thoughts. Layer by layer, taking shape. When you need your tools, bring them in. They just click. Okay, kick it up a notch. Create something smarter, something powerful. Style counts, so give it your touch. Big or small. Next idea hits.
This episode is brought to you by The Farmer's Dog. Dogs are amazing. They're loyal. They're lovable. Like, just having Marshall around can make my day 10 times better. And I'm sure you love your dog just as much, and you want to do your best to help them live longer, healthier, happier lives. And a healthy life for your dog starts with healthy food, just like it does for us. There's a reason having a balanced diet is so important. So how do you know if your dog's food is as healthy and as safe as it can be? Well, Farmer's Dog gives you that peace of mind by making fresh, real food developed by board-certified nutritionists to provide all the nutrients your dog needs. And their food is human grade, which means it's made to the same quality and safety standards as human food. Very few pet foods are made to this strict standard. And let's be clear, human-grade food doesn't mean the food is fancy. It just means it's safe and healthy. It's simple, real food from people who care about what goes into your dog's body. The Farmer's Dog makes it easy to help your dog live a long, healthy life by sending you fresh food that's pre-portioned just for your dog's needs. Because every dog is different. And I'm not just talking about breeds. From their size to their personality to their health, every dog is unique. Plus, precise portions can help keep your dog at an ideal weight, which is one of the proven predictors of a long life. Look, no one, dog or human, should be eating highly processed foods for every meal. It doesn't matter how old your dog is. It's always a great time to start investing in their health and happiness. So, try the Farmer's Dog today. You can get 50% off your first box of fresh, healthy food at thefarmersdog.com/Rogan. Plus, you get free shipping. Just go to thefarmersdog.com/Rogan. Tap the banner or visit this episode's page to learn more. Offer applicable for new customers only. When you say there's no information, like how are you measuring whether or not there's information in it?
So really in bits. I mean, the idea is, and I should say it's very much in principle. This, so no one thinks in practice you could reconstruct what I wrote down on this if you set fire to it. But in principle,
Well, maybe sometime in the future, maybe a million years from now.
in principle, you could just collect everything. Then somewhere in that all that radiation and ashes and light that's come off the thing is the information. It's there. So you could reconstruct the book or what I wrote on this page in principle. But the thing about Stephen's calculation was that even in principle, it said there is no information. And by the way, it's kind of easy to see why, actually, because this radiation, this Hawking radiation that comes off the black hole, it's coming from the horizon of the black hole. So I should say what the horizon is, maybe. So it's if you remember, I said that the sun, if you squashed it down within 3 kilometers of radius, you'd get this kind of distortion in space and time, from which, if you went in across this region 3 kilometers, you went inside it, you couldn't get out. So that's called the event horizon. So you wouldn't notice if you fell through the horizon of the black hole in the Milky Way galaxy. If you went into that one, we could be falling through that horizon now in this room, and we wouldn't notice anything, except that we couldn't get out again. And ultimately, in a few hours, in that case, time would end for us. So we just you go to the end of time. We could talk about that. There's a picture of that. Maybe I should talk about this. Is getting quite complicated already, isn't it? We didn't start in a relaxing way, did we? I don't know.
No need to. No need to. Let's get right into it. So we wouldn't notice.
Not for the big black holes. So these supermassive black holes, we could fall across this horizon. It's just like being in empty space for us. So we'd we would just be talking now when we could have been talking on the outside of the horizon, and by the time I finished the sentence, we could be on the inside of the horizon, inside the black hole. And according to Einstein's theory, at least, which is the theory that predicted them initially, we could just do that. We could just go in, and we wouldn't notice for a bit. The thing we would notice ultimately is you go inexorably. There's nothing you can do. You go to this thing called the singularity once you've crossed the horizon, and you are going to that thing. And then the question arises, what is that thing? And one answer is we don't know, but in Einstein's theory, it's the end of time. So one way of picturing what's happened here is so distorted is space and time by the collapse of a star or the collapse of loads of stuff to make these big supermassive black holes. We don't quite know how they form, actually, but it's collapsing stuff. So it distorts space and time so much that in a real sense, they kind of flip over. They get mixed up. And so this singularity, which you might have thought of as the point to which this thing collapsed, this infinitely dense point, you might think, but actually it's more correctly to be seen as the end of time, because everything's got mixed up. So you go to the end of time. And it's just like saying, why can't I escape that thing? It's like, why can't we escape tomorrow? Right, so we are going to tomorrow.
Right.
And if I said to you, let's run away from tomorrow, you'd go, I can't run away from tomorrow.
So is it the end of time because all information is being erased, so there's nothing?
Yeah, I mean,
is that the idea?
If you draw the thing, you can draw a map of it, and it just literally time ends, just purely in Einstein's theory. This is 1915. His theory of general relativity. You just get a line there, a line that says there's no future beyond this line. It just stops.
Okay.
So, I mean, admittedly, that's not. We think there's a lot more to it than that. But
Is it just we haven't figured the rest of it out yet?
Well, that's the thing. So we're starting to get hints about what might happen. which is leading us. So to backtrack a bit, why does this calculation Stephen did? Why has it got no information? Why does it say there's no information in this radiation? The thing is, it's coming from the horizon. So it's all one. There's loads of ways to think about it, but one way is that this weird place, this point of no return in space that you can fall through, but it's a point of no return. It sort of shakes. It almost disrupts the vacuum of space, and sort of almost shakes particles out of the vacuum. That's one way of thinking about it. But this radiation is coming from the vacuum. It's coming from empty space. Whereas if you think about the thing that I throw in, if I throw this notepad into the thing, then that goes to the singularity. It's got nothing to do. The radiation's got nothing to do with this thing. This thing's not. This thing is not set on fire or something like that. It's gone to the end of time, and just whatever's happened to it has happened to it. So this radiation's got nothing to do with anything that falls in at first sight, at least. And so that was the paradox. It's called the black hole information paradox. It's like it's one way to put it is the laws of nature that we use to calculate what happens tell us that information is never destroyed. And when you calculate what happens, it tells us that information is destroyed. So that's why everyone got interested in it in the 80s, because it's interesting.
So when we're looking at the structure of the universe, obviously there's so much still to learn just about what's out there, but what role do we think, like, is there a purpose? Is that the right term, like, for a black hole? Like, what obviously we know, is it still do they still believe that in the center of every galaxy there's a supermassive black hole that's, 1/2 of the mass of the galaxy? Is that what it is?
Yeah, something like that. Yeah, and that's there's occasionally a galaxy. I think one was discovered where we said maybe we can't see evidence of a black hole, but I think
really?
So there probably is. What
do you think that thing's doing there? Like, what is that? What's the what is the the structure is so insanely complex and so immense, and you see these things everywhere. And so what purpose do you think they serve in the universe?
So, I mean,
is that it might not be the right term.
Well, so I think I think I'm right in saying we don't fully understand why all galaxies, as you said, maybe there's an exception, but all galaxies have a black hole, a supermassive black hole in the center. It's obviously got something to do with the way they form. And one of the purposes, by the way, of the James Webb Space Telescope is to try to look at the formation of the first galaxies. So that's one of the reasons that telescope is up there. So it's cutting edge research. We're trying to understand how the galaxies form. But I clearly, you're right, that it has something to do with the way the galaxies form in the early universe.
Pulling in stars.
Well, they do pull in material,
right?
But if you've got stuff orbiting around them, it stays orbiting around it.
Oh.
So the way we first detected the one in the Milky Way, before because that image is very new that we have of it, is the stars orbiting it, very close to it. They're called the S stars that whiz around in these orbits very close to the black hole. So if you're just orbiting around the thing, you go.
Imagine that view.
Yeah, because
you think it's weird to look at the moon? Imagine if there was a supermassive black hole above our head.
It'd be so cool. I'd love to see one.
The moon is so cool. The eclipse was wild. We had the eclipse here in Texas.
Yeah, did you see it?
Oh, yeah. It was incredible. It's so strange. The whole day turns into night. All the birds stop chirping, and you're, like, staring up at this perfect eclipse. It was incredible.
Did you get this? Because I saw one in India, and I got this feeling that I was living on a ball of rock.
Right.
And it must have been just because the night just falls.
Right.
And suddenly you see the universe comes much more quickly.
I went to the Keck Observatory once in Hawaii. I've been a few times, but one time I went on the perfect night with no moon, and it was sensational.
Yeah.
It was the most. It was such a vivid image of the entire Milky Way, and every inch of the sky was covered in stars.
Yeah.
It was so phenomenal, and it made me a little upset. Because I was like, this is above our head every day, and this would radically shape the way human beings feel about our place in the universe.
Yeah.
It would greatly expand the curiosity of young people.
Yeah.
to explore space. So many more people would get involved in astrophysics. So many more people would get involved in just the exploration of the known universe because it's so majestic. And instead, we have like our screen is off. It's like that. It's like that screen. That's what we see because of light pollution.
Yeah.
That should be remedied.
Yeah.
Like that's not a good trade-off. Like lights are wonderful, but it seems to me like there's got to be a way to do this where you don't ruin the view of space.
Yeah, because
How about we play for who's the real Johnny Vegas?
Was your head always that big?
Your cards might as well be written on your forehead.
Are you holding cards or a tissue?
A world of rivals, millions to be won. Are you ready to face off? GG Poker. Download, sign up, face off.
you know these questions we have about our place, and as you said, it can be easy to be myopic, can't it? You
Yes.
said if you look at our screens, it's Earth that we think about at most. And most of us don't
Right.
really think about Earth. You think about your country or your city or your town.
Or your
So even-
neighborhood.
Even thinking about the Earth. But you're right. If you know when you look at that arc of stars, and as you said, when you see it in a truly dark sky, it's
Yeah.
powerful.
It's incredible.
400 billion suns, give or take. Right, 400,000 million suns.
That's just words.
It's
You know what I'm
impossible to
saying?
picture.
Yeah, it's insane. Your brain doesn't even process that. Like I could repeat that if someone says how many suns? Oh, 400 billion. I don't know what that means.
No.
That's
It's
so
well,
abstract.
And most of them, I think, the best guess would be all of them have planets. So pretty much. So you're talking about trillions of planets.
Now we're getting into my subjects. What is your take on all this UAP disclosure stuff? Do you give it any mind at all? Or are you busy with like real stuff?
No, I mean the thing is, there's a thing called the Fermi paradox.
Yes.
Which I think we talked about before
Yes.
on the show.
Yes.
And the paradox is that if we haven't seen it, let's assume we haven't seen any evidence of anything. That's a paradox because, as I said, we now know. We didn't when Fermi first posed it, by the way. We now know there's so many planets out there. So let's say trillions of planets in the Milky Way. The Milky Way's been there for over 13 billion years, pretty much the age of the universe. So if there's no one else out there, then the question is why? Because there's been so much time and so many places for civilizations to become spacefaring civilizations.
Right.
As Elon talks about multiplanetary civilization, we're very close to becoming a multiplanetary civilization. And once you have become a multiplanetary and multistellar civilization, if you become that, you're immortal, basically, essentially.
Right.
So the question is, the paradox is, why does it appear nobody has done that? So the first thing to say is, I would not be surprised, right? If a UFO landed here now in the parking lot, I'd actually, not only would I not be surprised, I'd be relieved, actually. Because I'd be like, this is good, because it'd be a weight off my shoulders, because I'm worried
Right. That we're the only ones.
we're the only ones.
That's
and
a terrifying scenario.
and we're going to make a mess of it.
Yeah.
And so I'm worried that we could talk about
But
that.
isn't it bizarre? Like one of the things that's fascinating about looking into the night skies, because it's so humbling, because it's so immense, it kind of puts everything into perspective, and it just gives you this like different view of the world. So the universe is so vast and so spectacular. Why is it so important that we exist? To us, it's so important that we exist. And if we make a mess of this and we wind up dying, the universe is so big. If we were the only intelligent life in the universe and it didn't matter, we blew ourselves up, like it's just a weird aberration that's attached to a survival instinct. Like
so-
we're a weird biological aberration.
So if you think about, let's assume. So we didn't finish the UAP thing.
Yeah, we'll
so,
get back
So
to
I
it.
was just
We'll
saying, yeah.
circle around.
So I don't know about that, but anyway, let's assume, just for the purposes of this, that we're the only ones in
Yeah.
our galaxy. Let's say.
Okay.
Then I would argue that. So there's a question I ask in these live shows that I do. I start with a question which is kind of a joke in a way, which is, what does it mean to live a finite, fragile life in an infinite, eternal universe? Which is a good question, right? That's what you're asking.
Yeah,
right? What
that's
does it
the real
mean
question.
to live this finite?
Right.
The first thing to say is meaning, right? What does it mean? That doesn't sound like a scientific concept in a way. Meaning,
Right.
I would argue that whatever it is, it self-evidently exists because the universe means something to us. I would argue that it's a property of complex biological systems. So whatever it is, it's something that emerges, in this case, from human brains. It self-evidently exists. Everyone who's listening to this knows that the world means something to them. So I would argue that if this planet is the only planet in our galaxy where complex biological systems exist, right, at our level, then it follows it's the only place where meaning currently exists in a galaxy of 400 billion suns. And therefore, I would argue, just for that very basic point, that we have a tremendous responsibility in some sense. Because by the way, I gave a talk, a little video thing at one of the climate summit, the COP climate summit in Glasgow in the UK a few years ago. And they asked me to do a little video to the world leaders. And I think they thought I'd say, welcome to Glasgow, have a nice meeting. But I made this little argument as fast as I could. I said it's possible, at least, that this is the only place where complex biology has emerged in our galaxy. If that's true, this is the only island of meaning in a galaxy of 400 billion suns, and you are responsible for it because you are the world leaders. Therefore, if you destroy it through deliberate action or inaction, then each of you would be personally responsible for destroying meaning in a galaxy of 400 billion suns, potentially forever. Now go and discuss that. Was my intro to Glasgow. Now, and we can all argue, because people will be listening to this going, this nonsense, how can it be? We can all argue about whether that's true. What I would say is, given that, as far as I'm aware, we don't have any good evidence to the contrary, which goes back to your previous question, it's a reasonable working assumption. So why don't we just operate on that basis? And then, if someone lands tomorrow, as I said, I'd be very delighted, because then what I just said would be false, and we could relax a bit and go, it doesn't really matter if we destroy ourselves to some extent. But so I think it's worth taking seriously the idea that civilizations are very rare. Now, and by the way, I used to say, probably last time I was on, actually, I used to say that in the far future, then the complex life will cease to exist. So it probably doesn't matter on a global scale, but it matters locally because of this idea that meaning emerges from complex biological systems. So if you don't care about that, what do you care about? But actually, I read a book. Have you had David Deutsch on the show? David Deutsch is a really interesting physicist.
I don't believe I have.
He's one of the founders of quantum computing, and so he's a big figure in quantum computing in particular, but he's a great thinker. And I was reading some stuff he wrote recently, and he pointed out that it's not necessarily true that life is temporary, because you could imagine a situation as you go into the far future. Let's imagine that we continue for 1 million years or 1 billion years as a civilization. Imagine what we could do. It is possible that life can get so advanced in the universe that it can start to manipulate the universe itself. So, or at least stars. He said you could imagine, for example, just imagine, really wild speculation, but imagine life gets so advanced that it can start to change the destiny of a star. Maybe it could start to add material into the star or something, whatever. So we don't know how to do that, or if it's possible, but imagine it could. Then the evolution of stars life would matter, in the sense that it could start to change the way that the universe behaves on a large scale in the future. And so it reminded me, actually, there's another great book by John Barrow and Frank Tipler called The Anthropic Cosmological Principle from the 1980s. It's one of my favourite books, actually. And I remembered it. And in there, they speculate about this life in the far, far future. And if it became powerful enough to manipulate the whole universe, or the observable universe, then suddenly you can't make predictions about the far future unless you consider the possible impact of life on the universe. And whilst this is, I should say, it's wildly speculative, but it's actually logically, it's quite an interesting point. So I kind of disagree with myself a few years ago, where I would have said that life is extremely valuable because it brings meaning to the universe, but temporarily. And so it brings these brief, like, flickering candles of meaning, and then they go out again. But it's worth considering. It might not necessarily be true that if you really think, I mean, just to say, I mean, it must sound to many people listening just nonsense, right? Science fiction. But if you think our civilization has been around for, 10,000 years at best, really, give or take. And in that time, we've sent stuff out of the solar system. Although we don't yet, we're way away from being able to manipulate stars, we can manipulate planets. So we are changing the way this planet operates. Life has changed it. You know, the oxygen in the atmosphere, before we appeared, the oxygen in the atmosphere is a product of life. So life already, we know, changes planets. And so I like that speculation that just possibly, it's not just a temporary little phenomena that flickers in and out and then disappears again. It could have a real bearing on the future of the universe.
And you could also make the argument that intelligent life might be the universe's way to